was very little time. So let's see. Do you hear me well? I try to speak louder. Yes, I will talk about a theory, namely about how we try to find a good way of doing predictive calculations for nuclear structure. So we address the problem of accurate computation by developing what we call generally relativistic nuclear field theory in the model-independent equation of motion framework, using most universal language of quantum field theory, and as major tool, fermionic correlation functions. The advantage of having this general formalism is that we can derive all the existing models from it and connect them. So the theory is thereby transferable across the energy scales. It finds rhymes in high energy physics, in condensed matter physics, maybe also in solid state. It's capable of identifying the bottlenecks of the existing approaches and opens the door to spectroscopic accuracy, as we hope. In this formulation, just to tell you in advance, dynamical interaction kernels of the fermionic equations of motion are the source of the richness of the nuclear wave functions in terms of configuration complexity. And a variable configuration complexity offers the way of quantifying uncertainties in the many-body domain. So I will focus heavily on the theory and then I'll show some selected highlights. Nucleic solid states, and maybe if there is time, I'll talk about some open problems. So let me start from showing this.
You click once on the screen. Yep.
Showing this famous picture of the energy scales that I have extended all the way to Planck. And typically we
try to get rid of the hot message. So cannot find the mouse.
As you said, you have to move it. It's a good separation of scales, but actually we see that nuclear structure is sensitive to various scales, and rather than disconnecting them, we have to really look at the connection. So the major conflict here is represented by so-called emergentism and reductionism. So we want to know how big things are made of small things, but there are emergent phenomena which we cannot always trace down to the next scales. And that tension is sitting in the very nature of the Newtonian. And there is always this trend to identify new degrees of freedom, and then that drives us to the next energy scales. So our interactions are inevitably built of some free motion, and up here at the very high energy scale, actually there is no interaction. So there is everything is made of merging and splitting strings, and that's probably a hint behind that finally we have to understand all these degrees of freedom. So the potential solution to this tension is just keeping or establishing connections between the scales by emergent phenomena, and that's why we try to be as microscopic as possible. So this is the picture of how we view the nuclear-nuclear interaction. That's a relay, or you can say tower, but actually it's passing information of different energy scales, so high energy, intermediate, low energy, and in principle, each process here is calculable from the underlying scale, but there is always an almost. So there is always a little bit that we cannot control. So yeah, in this context, I'll talk about ab initio many-body theory that assumes a generic, unspecified Bayer interaction as an input, and the theory will be essentially model independent, including all the channels, but then we see how models are falling from that. High orders of the interaction that we use on the tree level will be treated via in medium propagators, and we try not to use perturbation theory. So that would be just formal part. So we use some unspecified interaction. This will be given by this block. But implementations, when we talk about realistic implementations, the situation changes. So in many cases, we cannot keep the entire volume of correlations that are identified by the many-body theory, and we have to do some compromises here. So I will concentrate on the meson exchange interaction at leading order, and then show how we actually employ effective coupling constant masses adjusted on the nuclear level, the mean field level, from which we can do fully self-consistent theory valid across the nuclear chart for all phenomena and without changing the coupling constants. So there is an ongoing work which uses the Bayer meson exchange interaction, but this is not ready yet. So we have as a goal to be as fundamental, feasible, and predictive as possible. And let's see how it looks like. So we start from the Miltonian that's written here. It's given here in a relativistic form, but it's very similar in the operator structure to a non-relativistic one. And I omit higher body forces for now, just two-body interaction. And that's essentially the input. So this little V bar here, the anti-symmetrized interaction of two fermions in the vacuum, and we try to stick to that. So we look at the operator strings. Here's the simplest fermionic string, just a particle propagator in the background of the ground state of the many-body system. So here are the notations explained. So the number index is a representation index that can be coordinate, momentum, and it includes time. So psi bar is just conjugate spinor, and the bracket is the ground state. And remarkably, if we look at the Fourier transform of this object, it's a function of one variable. It has this very simple pole structure, and that gives us direct access to the observables like energies of single particle states that are poles here, and spectroscopic factors that are formed by the residues. Similarly, we can do particle Hall. Similarly, we can also transform particle Hall. Okay, I'm hesitating to say propagator, we call it propagator, but at the same time, it's a response function. The jargon for this kind of bracketed operator strings is correlator, but essentially we took them as two-point functions. So depending on two times, like here, and that's for a reason also, because this response function will be contracted then with local operators, so we don't really need four-time function here. And just because of that, it has a very similar spectral expansion. The residues are now transition densities, and the poles are the excited states. So let me explain, because I expect there are some experimentalists here in the hall, and maybe many body theorists who are not familiar with annotations. Let me explain. So we don't operate Feynman diagrams in the original sense. We do everything analytically, but diagrams are good to represent the results. So a single thin line is uncorrelated propagator, thick line is correlated. So what's uncorrelated is typically known. That's the So we can do a similar mapping of a two-fermion propagator, particle hole or particle that is here. And that will be two fermionic lines bridged together by a box. So if you see a box, this is now three-body. That's something where everything can happens. So that's something we are aiming at calculating. And the known input here is this two-fermion interaction in the vacuum. And usually we have an idea about uncorrelated propagator. Everything else is expected to be calculated. So if you're an experimentalist, you can imagine this is a cable. This is a cable that connects your devices, and that's something you understand very well. This is some elementary device that you also understand very well. And all other boxes represent the processes where everything happens, and that's something you want to measure. So that's how I can make an analogy. And then the sums typically they have these indices that they match, and matching indices are your connectors. You connect your cables to your devices by matching the index here. So that's the closest analogy. So then how we do exact ab initio theory. Based on that, we just generate equation of motion. So that object is differentiated with respect to time, and that gives us the Dyson equation. That's the famous equation in the operator form here. And again, G naught is free propagator, and all the physics is sitting here. That's irreducible kernel, also called self-energy. It includes all the processes that happen to the particle in the medium. And the self-energies have two components. One is static, non-dependent on omega. Omega is energy, we call it frequency here. And the other is energy dependent or retarded. That's why we put an R here. So the first one is formally looking like a Hartree-Fock, but with a correlated line here. And the dynamical one, the second one, includes now a more complex propagator. So this is a two-particle, one-hole propagator sandwiched between the two interaction matrix elements. Essentially, that's an ab initio DFT, because the total energy can be calculated by the famous formula from just this single particle group. So that's a dynamical version of the DFT, because the static limit of this propagator is the density. So that's a correlated density. But the irony here is that you cannot really disentangle these two, because this density is the static limit of G, that's the full solution. So it has a feedback from the dynamical term, although itself it represents the static term. Usually what DFT does, it neglects completely this part if it's non-adiabatic theory, and assumes some density dependent of this interaction instead. But this term actually represents very important dynamical effects that form the structure of the nucleon. As I said, similar spectral expansion appears for the particle Hall correlation function, and also similarly the equation of motion looks like a Dyson. It's actually beta cell beta regulation that's simplified the Dyson form because of one variable only. But this analogy is very useful because, again, we see free propagation of two fermions and then a self-energy that's now called two fermion amplitude. Some people call it self-energy still. And that quantifies the in-medium interaction, because actually this process is nothing but the scattering of two fermions, scattering amplitude of two fermions, but in the correlated medium. And again, it has two parts, one static that comes with a delta function, which means instantaneous, and the other is retarded, time-dependent part. And that's colloquially associated with short-range correlations, and the range is the same as the range of this interaction, which serves as an input, but it's now addressed by two body densities. So these boxes here are two body densities for operators, expectation value, and the dynamical part contains G4. So that's the propagator of 4 fermions to particle to Hall. Actually, if you open the book of Selevinsky and Volya, there is a very elegant formalism how this operator equation of motion works for a single operator. So if you master, understand how to do it for a single operator, then you can put all these operators together, and you will see that the dynamical part will always contain two ranks higher structure than your initial operator. So if you track one operator, you generate 3. If you track, now we track 2 operators, we generate 4, and so on. And that's how this hierarchy is growing. And that what makes the nuclear many-body problem or strongly coupled many-body problem tractable. So I wanted to acknowledge the role of Peter Schock in this work that we did with him some time ago in formulating this framework, although it was not new. It was largely based on the previous development, we just put it together in a different way. And typically, if you look at textbooks, you will see this as Schwinger-Dyson formalism, where this non-static part or dynamical part appears in a different form. So you wouldn't probably recognize that. And that's what we call symmetric form of the kernel. And that particular form is especially useful for approximate treatments and for deriving the known models from this general frame.
So,
yes.
Yes. I have a question on the previous slide on your kernel about the Fock term. Naturally, I think it is energy dependent, so I would put it on the second part.
Yeah, I'm trying to find it. Sorry.
Yes.
So Fock. You mean Hartree
yes.
Fock? This one.
I would put it in your figure equation on the right side because it's energy dependent, but problems to find it in the diagrams.
Well, Fock term, I mean, in this interpretation, maybe it's a different interpretation. In this combination, the Fock term is sitting here because this is antisymmetrized.
Yeah, okay.
So, and it's not energy dependent. I mean, it's non-local. It's non-local if this interaction has this ability to be non-local, but it's not energy dependent.
Okay, so you put it on
yeah, it's that, yeah. So there are 2 terms here, is Hartree and Fock stems from the fact that this is antisymmetrized. Very good question. Because Fock term is a big story itself. Yeah. That's right. So I wanted to make some language remarks since I started to say ab initio. I went on a shaky ground. So, there is no ab initio theory. Even the standard model, as we know, most fundamental theory we know is not ab initio. because it has parameters, it has non-calculable parameters, and there are many open questions. These big, beautiful questions you all know about. So, okay, I will not comment. That is just to illustrate the fundamental theory as we know it now. What we call ab initio in the theoretical physics across the many fields is when you're able, starting from bare interaction in the vacuum. I'm showing two body bare interaction. It can be three body to you start from only that as an input, and you are able to describe a many body system. So that's the language theoretical physics typically gives us. So if we are not able to do that, we have to adjust, readjust, refit, fine-tune parameters on the way. So that's technically not ab initio, that's called effective. And these two are semantically in opposition. So then sometimes we say UV complete, but this is also not totally true. I mean, it's UV complete up to the knowledge of the bare interaction. So that's the sense I'm using. And then further, I wanted to actually continue to this common confusing narrative saying that there is an ab initio theory and there is traditional. Or there is the theory, that's chiral perturbation theory, potentials, and there are models, which are the many body approaches. Or there are equally good many body solvers that are some unimportant attachments to chiral perturbation theory. Maybe it was not meant like that, but it sounds like that. And I think these are equally wrong. And also quantified uncertainties can be provided outside that. So I'm just putting this as a reminder, but I want to say in explanation to this, we can formulate ab initio theory, but it's very, very difficult to implement that accurately. However, even working with effective interactions, we want to see an ab initio theory as a roadmap because it constrains concrete implementations, for instance, maintains the necessary algebraic structure, like, for example, this division into static and energy-dependent interaction. Moreover, all traditional, so-called traditional microscopic manipulative models that employ various interactions where effective, soft, and whatever interactions, they actually are derived ab initio, as we have shown. And they just represent various approximations to the static and dynamical kernels of the same equations of motion. So paraphrasing Weinberg, we can say, like he said, all non-renormalizable theories are as renormalizable as renormalizable theory. That was a famous. We can say that was in the Dyson sense, in the Dyson sense, we can say traditional theories are as ab initio theories in the theoretical physics sense, just depends what path you follow with implementation. Okay, I think I'm too slow. Let me just check. Okay, 30 minutes. So we start for the interaction, we start from underlying scale because you know underlying scale governs the physics on the given energy scale. So we understand quite well the hydrodynamics. These are diagrammatically the terms which describe nucleon scattering in principle. Bond potentials are like that, and so on. And I wanted to put also the chiral T here because it's a very well-known concept. And that's on the tree level. So what happens beyond the tree level? I'm trying to reflect here. So we have this, on the right-hand side, we have this subleading orders, so-called, that are totally belonging to the vacuum. So this is all calculated in the vacuum. However, we know that these propagators have to be addressed if you go to the medium. So basically, then it's paired with the many body solver, the question mark, because I'm not sure it's a totally theoretically justified. And besides that, standard solvers, as we know them, they are very simplistic. There are no good solvers. I mean, all of them have to be still developed. And there is no good link between this vacuum power content, for example, and the power content that's formed in the medium, and that's what we were trying to address also. Basically, what we say when we compare to this procedure, when we just stick to the tree level and develop all the beyond tree level in the medium, we see the emergent power content that's associated with new scales of low energy collective modes in the big systems. So all I'm saying today is about big systems. Probably few body systems are different. But I'm talking about maybe oxygen up. Something like that. I would put the name. So the systems with sensible collectivity. So there are many questions in both scenarios. But I wanted to highlight that particular phenomenon of changing the scale, because when we go to a medium correlated, in the medium of a correlated nuclear system, the scale is again different. So next, I'll try to explain how we deal with this operator strings that appear in the dynamical framework. This can be done by cluster decomposition. That's also a scenario that was elaborated by Weinberg. That's a typical QFT procedure. So we just factorize them and list all the factorized terms. That's similar to weak theorem for non-correlated. So, and here there are different terms which are associated with different rank. I call them a rank of the relation function. So the first term, this is G3 and G4 because this appears in the single particle. So first term is only including single fermion Green's function for propagator. So the next we retain the two fermion configurations and then everything else. And we can roughly sort them out by the coupling regime. So weak coupling, this dominates. Intermediate coupling, this probably dominates. Not dominates, but becomes important. And the strong coupling, like UCD, we have to take all of them into account. So I will be staying within this intermediate coupling idea here, which means that we can roughly break these large bricks into small bricks and have these two-body correlation functions wherever they appear. And then something remarkable. Just formulate. We can actually see that these correlation functions, two fermion particle-hole and particle-particle, they appear in combinations with two interaction matrix elements, and that can be exactly mapped onto the collective modes. So there is no approximation here. So approximation was done here when we cut out the higher with the higher rank propagators, but this is exact. And this signals emergence of low energy pseudo non-Bogostan bosons, so that we can interpret them like that, because they are associated with observed symmetry breaking in nuclei. For example, rotation symmetry, U1 symmetry that induces Cooper pairs, and that's emergence of superfluidity. That's the emergence of the sound modes. They are known as sound modes in solid state, but in nuclear physics we call them phonons. And the quadruple, octuple, whatever phonons, they are associated with this, the rotational symmetry breaking. And remarkably, they have very low energy. So that's why they become most relevant. So this type of mechanism we call quasi-particle vibration coupling. And that was known from phenomenological theories like nuclear field theory in the past. But similar formalism is applied in hadronic physics to address diquark or meson structure and so on. So that's essentially universal. Similar phenomena are seen in condensed matter physics and so on. Yeah, this is what I wanted to illustrate here. So basically our self-energy is becoming as radiative correction time contributions plus some remaining just 3 fermion part, which is usually not really well expressed in nuclei, but most of the contribution is given by this two. And this is regular and pyrene phonon, which can be then unified in the superfluid theory that I'll show next. And what's interesting here is that they generate these vertices that topologically look like the standard model interaction vertices. And that's the idea behind that. Basically, we say if we can derive these vertices, there's probably something underlying going here. On the nuclear structure side, this concept was also known. This was elaborated by nuclear field theory. Ricardo Broglia, who recently passed away, made a terrific contribution. And Vadim Solovyov, yes, the Dubna physicist who developed the quasi-particle phonon model. And essentially it says that the Hamiltonian can be rewritten in a way that it contains new bosonic degrees of freedom that are associated with this quasi-bound states of 2 fermions. And then the system looks like a system of fermions and bosons. But the contrast with the, for example, solid state is that these bosons are made of fermions. So they are not independent of degrees of freedom. So now I'll try to be faster. I deliberately spend more time on the stuff. So superfluid theory can be formulated for this correlation functions when we allow all of them to be present. So we can plot them as these weird diagrams, but they can, you have to believe me here, they can be ordered in a way that the dynamical self-energy is rather compact, and especially it can be compactified after the Bogoliubov transformation. This whole thing looks like a single diagram, the quasi-particle basis, and all the complexity from superfluidity is transferred to this vertex functions. So we did that for the 2x2, the most famous 2x2 Gorkov-like formalism, and now recently we did it also for 4x4. That's required for the temperature-dependent theory. So 4x4 block matrix structure. I think it will also be valid for 0 temperature if you go beyond the traditional Gorkov theory. and so on. I think I can skip that. Now I'll talk about implementations. So what we can calculate and what we cannot. So for the nuclear response, I will focus on the nuclear response. So we calculate this correlation function that I introduced, and that's the grammatic form of the equation. This is the operator form. So there is a free, quasi-free, that's the mean field propagation of two fermions. Then there is interaction part and statically dynamic. So the static part, that's just our meson exchange on the tree level, can be parameterized or addressed by the densities. And here's the dynamical part, which is responsible, as I mentioned at the beginning, for the richness of this spectral strength distribution. When we use effective interaction, we have to use the subtraction to avoid double counting. We use the interaction developed by Peter Ring and his group. For example, there is a review, I think I missed the reference here. There is a review paper that explains this whole concept. It's more known like covariant energy density functional, but we only use it for the basis, as a basis and for extracting the effective interaction. So this is going beyond DFT. And on this level, you have the famous quasi-particle random phase approximation, QRP, and that will be the extension. So that's going beyond QRP. And we have now universal labeling, relativistic equation of motion. There will be 1, 2, 3. So QRP represents configuration complexity variance of it. So this phi amplitude, the dynamical phi amplitude after projecting the collective modes looks like this, and that's the content of the traditional nuclear field theory, just for single phonon exchange diagrams. And then our formalism allowed for an extension. Particularly, we have correlation functions here. And these phonons can be then iterated. So they can be calculated in principle exactly. So they are not necessarily QRP phonons. So that's the idea here. Because this equation of motion for the two-body has two-body correlators in a closed form. So it can be but it's not easy because technically we have to calculate this response function that's going here for each multiple on this level and then plug it back into this plane. So we were able to do 2 iterations so far. After that, if we expand, actually we do it non-perturbatively, but it can be expanded perturbatively because if you want to talk about vowel counting, then you have to do some analysis in terms of perturbation theory. Now perturbation theory is done with respect to the quasi-particle vibration coupled the vertex. So it's not with respect to the barrier interaction anymore, because as I said, there is a new order parameter. And if we expand our non-perturbative series, we can see that this contributions, for example, are automatically included in the iterations. But we don't evaluate this term by term. This is included automatically. And after that, we don't do much. Theoretically, and again, I omit all this area about two-body operators, so on, just simple one-body operators. They are contracted here, and that's how we calculate the strength. Because we want to now connect with some observable quantities. So we need to connect to certain people, and that's monopole, dipole, and high multiple resonances. We can do common So we can also do static properties. And what's essential here is that what I will be showing will look like strength distribution. We usually have some small imaginary part of the energy for representation purposes, and that would be the width of a single peak. So this will be our input here, but the calculable width of the total resonance is much larger. So this is how it works. And the next slide explains the fragmentation effect. So in principle, the spectral expansion is exact. It only depends on the correlation content that you can put in the excited states. But when you include more and more correlations, we see it populates more and more states. For example, on this level, there's just bare mean field particle Hall propagator. We see one state. That's just energy difference between the two. P is like one state in the spectrum. So then we include coupling to one phonon configuration. And one phonon is technically correlated particle Hall pair. That's why this is 2p2h, or 2 quasi-particle plus 1 for 4 fermions in total. And we get fragmentation because there are more possibilities for these images. So 2 quasi-particle. 5 minutes? Yeah. So then we include more. So we include more, there is more fragmentation. So, and that formula explains actually how. So this is the giant dipole in calcium. So we have now three levels of configuration complexity that's represented by black, blue, and red. So we can compare to data here to the green. The symbols, these are data. And then, as I said, we have small, relatively small, here usually it's even smaller, smearing parameter, but the resulting gamma, the resulting width of the resonance is much larger, so it's many overlapping states. So we could do it for pygmy resonances and see that also it goes in the direction of data. We could do it recently for moderately deformed nuclei, so it's similar hierarchy shown here in comparison to data, and we can do it with much smaller resolution also. So this is high resolution picture. So recently it was pushed a bit to higher mass. So this is giant dipole resonance, and we can also do soft resonances in T120. So we can see that, again, we get some improvement. And more importantly, this, I mentioned that this gives uncertainty quantification. And that's because these approximations converge. They converge quite fast. So from 1 to 2 to 3, you see between 2 and 3, there is much smaller difference.
Sorry,
do you have a question?
Yeah, what's the difference between 1, 2, and 3?
1, 2, 3.
Yeah.
So this is described by this diagram. This 2 is this diagram. 3 is this diagram. So more configuration. So some calculations we still do. Okay, and I wanted to mention we can do this nice pictures of moving densities because these are our transition densities here, and we can put them together in time-dependent way. So just single highlights here. This was about GDR. For the monopole, giant monopole resonance, we did calculation showing that actually coupling to quadrupole vibrations is important, and it gives a good description in so-called soft nucleus pieces like 20. There was some more. And then we investigated pygmy dipole resonance at 120, and also the neighboring isotopes. It was a big systematic work. This is just a single snapshot from it. So we analyzed the pygmy dipole resonance. Particularly, we were able to identify two components in it. And the proposal now is that only the lower part is not associated with skin oscillation, skin mode, and the higher line part is more of a mixed character between skin and isovector dot. Okay, there are more pictures like that just for the theme, so we can do single modes, coupled modes, and we can do some funny. So on the REOM2 level, we can do charge exchange. So these are some results from the past. Fragmentation of the gamma Taylor resonance particularly gives the opportunity to accurately compute the beta decay rates over lifetimes. Also here, but for this type of resonance, we either can look at the strength distributions that are possible on the stable nucleus side. And they're not beta decay, or beta decay are unstable, so we cannot see strength distributions. I mean, we can, but it's, and we could do also some calculations for GT plus GT minus, explaining some puzzles from experimental. This is a more recent work. We looked at M1 transitions. So M1 transitions are special. I think that's the last I will show you. Yeah. M1 transitions are very sensitive to the pion exchange. And that's very difficult to describe in a self-consistent way. Because pion exchange has a very specific behavior. It has especially if you do it with the pseudo vector. But on the other hand, isovector mesons like pion and rho meson, they are known to come some smoothness. So we always see relatively weak interaction in the unnatural parity channels. Basically, what I want to say, most of this theory, most of the states that we were able to capture by the theory, they are generated by computation mechanism. So very little comes from the residual interaction. So this was motivated by the work of our experimental colleagues from FSU. They analyzed previous data on titanium-50, previous data from different reactions, and what they did, they measured DP reaction on titanium-49, tracking a specific spectroscopic factor that's associated with a neutron hole in 1F7 and 5 because this was supposed to be the driving force of the low energy part of the magnetic strength function. This was actually only seen here, predominantly seen here, and they didn't see anything. So this was interpreted as no correspondence between the spectroscopic factor and the large BM1 strength. However, we had three theory approaches here: shell model, quasi-particle form model, and our approach, which all had reasonable BM1 values. However, spectroscopic factors were not all in line. For example, in our approach, we saw that it did not this data, QPM similar trend, and the shell model was suggesting the opposite. So this is still remaining a puzzle. Why do we see this kind of coordination between the spectroscopic factor and PM1 strength at low energy? It remains challenging, and so more is to be understood about ion exchange and ground state correlations, probably two body currents here. Okay, so I'm going to finish. I think I have half of my slide, but if you want to know more, if we meet in the afternoon, I can tell them. So that's all.
Are there any questions? You, Elena?
Thinking again about ab initio
Yes.
nuclear physics, ab initio nuclear theory, how many parameters would be needed to calculate these REAM predictions? How many fundamental parameters from the theory would go into comparing to experimental results?
It depends on how accurate you want
Yeah.
them to be. Currently, I think we don't, I mean, the short answer is we don't know. The long answer would be that what we are trying to do, we are trying to start from here,
So
this level. So the number of parameters is associated with the number of mesons that I included.
okay.
So simplest, you can do it, as I said, you can do it from starting from the bare meson exchange that describes scattering data, like bond potential. As I said, we only do 3 levels, so we pick it on 3 levels. We don't do the loops in the vacuum. We do all this in medium propagation in a correlated way, without introducing parameters. So we want to keep all the parameters intact. So this would be then, I don't know how many parameters are in bond potential. There are 6 or 7 mesons. And I'm struggling because I don't have these results yet. So what we calculated were with effective mesons, and has a little bit less. It has sigma omega rho ion. That's it.
The interaction is between a meson and a nucleon.
So we have, for each meson we
meson
have a mass.
interaction.
Yeah, we have a mass and coupling constant.
Mass
So
and
that's
coupling constant.
And for this Valichko type model, we need also 2 parameters associated with either you can do nonlinear meson exchange, which has to do with meson self-interaction, like that's like gluon self-interaction.
Yeah.
Or you can do density-dependent meson couplings, which I'm not a fan. So I think that nonlinear meson coupling is more physical because we know the processes which are behind that. And density-dependent is rather random. It's like fitting properly. Some random functions. Then you need more parameters. Of course, we see if there are more parameters, the accuracy may be better because you have more ways to fit. But we want to see how much we can do and how good without touching. But of course, there are many different strategies. From what I remember, there are people doing chiral interaction, using chiral interaction. Yeah, I think there are 20 parameters. So there are.
Okay, on top of the hour, I will allow maybe 2 very quick questions. If
there are any.
What are the ranges of applicability and energy of this this approach, and can you go into the continuum, like above single particle thresholds?
Yeah.
For example?
I think we can safely go to 100 MeVs. This gamma of Taylor I was showing was going up to 500. So we don't probe the fine production here. Up to there, I think relativistic theory can be.
Chilling.
Yeah.
Kind of still about the movie, the time dependent, the slides for the movie, the oscillations.
Yeah.
I'm just curious because you show those very nice videos. How do I make sense of it? It's very non-trivial because you include a lot of fragmentations. But how do I compare those movies with, say, just a simple time-dependent Hartree Fock?
Okay, what we can compare to time-dependent Hartree Fock is.
Yeah, those movies. How do I make sense of it?
So I think this would be now the small amplitude limit of time-dependent Hartree Fock. That's QRP.
So you think that's similar?
Hartree Fock variable. This one.
Okay.
So this one has all the beyond Hartree Fock.
Yeah, so just in terms of the movie, how do I see the difference?
Well, I think we have to stop them.
So this the second one.
Okay,
the
let
one
me go. We have to stop them, otherwise it's not easy. They are not really very instructive for comparing. I think you see more when comparing these distributions themselves. Because basically what happens is that you can notice this is large amplitude, right? They are more far apart than here.
Right.
And this is because this peak is higher. So that's roughly proportional to the square of all the transition density. This peak, so this movie is corresponding to this distribution at the peak. And this movie corresponds to this green distribution at the peak. And actually, if you analyze the density values here, you can get some pretty unrealistic, very high densities if you don't include correlations. They're just too wild. These observations are too. But they are more for fun. I think they are not for serious, for serious analysis. I think we see more. But what we look at also, we look at the radial transition density distributions when we quantify them. For example, neutron skin oscillation, we want to see. I can show you what we do there. We do this type of plots. So we do this type of plots, state by state. For example, this is a low line strength in T120. This is the pygmy mechanism. If we want to see proton and neutron transition densities relative to each other. So this is for a simple approach. This is and for instance, this helps to identify the skin movement. Neutrons are blue here. So this is a proton oscillation, this is a neutron oscillation at this particular energy. And when we look at that, we say this is definitely a neutron skin oscillation because at which T stands it is, and it's going beyond the nuclear radius, right? I still see a question in your eyes.
Yeah, I can talk to you later.
So, and then we see, for instance, here we see that when we combine this with the component structure state, we see the summit mixture from the GDR comes when the distributions become shifted with respect to each other. So they're in phase here essentially, and without the phase here and so on. I think this is more instructive than.
Okay, we're a bit over time, sorry, because of the technical issues at the beginning. But let's thank Elena again. There will be coffee with Elena after lunch, so at 1 p.m. with the grad students.
The lead right. Well, I need to be there, but let me be in front of him.